Welcome to Mining Now. I'm your host, Jared Downey. Today we have Optiseis. They are back on Crownsman, but on a separate show. We're going to be focused, we're going to have Optiseis back, but we're going to be focused on mining now. I'm going to read this because it's technical, and I want to give you a quick summary before we jump into some of our tour and announcements. So we're going to be talking about the application of seismic method in mineral exploration, Optiseis software capabilities for optimization of seismic surveys for various surface conditions, and seismic application in the carbon capture and storage industry. It's going to be a technical industry. We've got a CTO on and a software manager on the show from Optiseis today. So it's going to be quite technical, and we're going to learn a lot. Before we jump into it, though, we are doing our heavy industry tour. You've probably seen episodes from Africa, Australia, of course, the US and Canada. We're going to places like ConExpo and CIM and PDAC and Indaba. Tons of fun. And if you want to join that heavy industry tour, you can let us know. It's info@crownsman.com. We'll put that up on the screen and in the description. You can email us. If you're going to some of these big events, just let us know and we can book you in for a spot. We do not get all over the world without support from our sponsors, and our two main sponsors for the heavy industry tour are Savinaw Equipment, helping you get mining equipment from all over the world to all over the world, and Corporate Traveler Canada, helping companies travel the globe simpler, faster, easier. So two very fitting sponsors for the show. With that, let's jump in. We're going to have Alyson Birce. She is a software manager at Optiseis. Mostafa Naghizadeh. Sorry, Mostafa, I didn't your last name. He'll correct me. And he is the Chief Technology Officer. Let's start with the correction right away. Mostafa, how do you say your last name?
Pronounce it Mostafa Naghizadeh.
Naghizadeh. I had it right and was practicing before we started, and then I still butchered it. So my apologies. Okay. Mostafa, I want to start with you. A lot of people would have seen Optiseis on the show before on our energy series. But can you just give an overview of who the company is, and then we'll sort of go into the mining specifics following that?
Yeah. So Optiseis is in nature is a seismic acquisition design company. So the company was founded 11 years ago by Andrew Crook and Cameron Crook, our founders. And we've been active in several regions of the world. Like if you look at the map, we have like plus 40 clients all over the world that we design seismic surveys for them. So while our main task is designing seismic surveys, we also do the later stage processing kind of QCs of seismic surveys and also interpretation of those data. And that's because these are all comes to hand. You need to acquire the data, you need to process, and you need to interpret. And being able to do the right design, you gotta be having a good handle on the processing QCs and interpretation QCs. We are not really seismic processing firm or interpretation firm, but we do those tasks internally to make sure that we design the best and ideal seismic surveys for our clients.
On those different stages, does Optiseis step in? Can they step in on all three stages? Can you step in? Like if they already have the seismic data, can you with that?
It's yes, like the seismic surveys, they usually, like most of the clients end up doing several times seismics on their assets. So if they have previously acquired seismic data, we just ask them to send us those data. We analyze them. We look at their targets, how at what depth they're looking to image the subsurface, and we can always use that. While during the survey acquisition, we always QC the survey results. We make sure that everything is going as theoretically planned, because when you go to the field, things start being like a bit difficult. You hit barriers, you hit rivers or mountains or slopes. So we always make sure that our seismic, we give them the right guidelines where to put the seismic sources and receivers. And then again, processing, that's pretty much its own different task, but we always use those previously acquired data to make sure that we design the right survey for our clients.
Clients, what about industry? Again, we're going to jump into the mining specific, but what's sort of the breadth of the different sectors that you'd say?
Yes. So, like historically, Seismic is pretty much well known for oil and gas industry. So you can't find any oil and gas company like the development and exploration that they haven't done seismic. It's pretty much very routine task for them. They have to do seismic exploration on their assets and make sure that they're hitting the right targets. So, but then again, the whole nature of seismic is all about imaging what's going below the surface. So in subsurface, we want to understand how the geological layers are located. So then this makes it like we can apply this one for other industries like mining. So mining is they're also looking to see what's going on beneath the surface, and they want to understand where their mineralization is kind of extended and find the extent of it and the location of it. So seismic can pretty much do the same kind of imaging for them and brought some like image that they can use for their exploration purposes. And the other one, the new clean technologies like let's say geothermal and then like carbon capture sequestration and the wind farms. Like you want to really know when you're putting your wind turbines, you're putting on a stable ground, and there's lots of needs to make sure that you have the right ground picked for those. So seismic can help in those industries to come up with the like right plans for their exploration and also developments.
Yeah, thank you. Yeah, so I mean, people see them as sponsors, so they'll ask me, kind of who they are, what they are, and just trying to understand the scope of the company. So Savinaw Equipment is a mining supply company, and they're delivering on the whole equipment supply chain. So everything from the ore processing to underground mining, open pit. They're in hard rock and placer operations. And what they're doing is they're sourcing equipment from all over the world and then delivering it all over the world. Now, they are a Canadian company, so they're based there, but, let's say, I mean, they're selling entire ore processing plants. So there might be a plant down in Latin America, and there's a new mine that needs that plant in Africa or somewhere in the US. So they're facilitating that entire transactions. But they're also delivering, an individual conveyor or a concentrator or a pump package or just an electrical package. So it really is the whole gambit of the mining equipment supply chain.
Fender Dunlop Usflex belts are engineered to withstand the harshest applications, delivering benefits that solve customer problems via superior rip, tear, and impact resistance. Usflex are extremely strong and robust belts that are difficult to destroy, which is important for heavy-duty bulk material handling environments. Made in their very own North American manufacturing facilities, this revolutionary concept in straight warp conveyor belting is up to 3 times more impact resistant versus competitor belting. Usflex users use fewer belts per year, make fewer belt repairs and replacements, reduce or eliminate belt downtime, and improve employee safety. You can visit FenderDunlopAmericas.com to learn more about their premium Usflex conveyor belting. The CIM 2023 Convention and Expo is coming to Montreal from April 30th to May 3rd, so join us in recognizing your peers at the annual CIM Awards Gala. This year is extra special because CIM is celebrating its 125th anniversary. There will be special programming and perks for exhibitors and attendees alike. Registration is now open and tickets sell out fast, so visit CIM.org to register now for short courses and explore sponsorship opportunities.
Could you give a couple examples in the mining space specifically to sort of paint the picture for the audience of the application, what you're referring to, you referred to earlier?
Yes. So I have these slides that so when we're talking about the mining, the mine can be in different shapes. So they can be in a hard rock environment. These are the volcanic rocks, and the kind of like things that the structures that you're looking there, they can be near vertical and veins, or you can have sedimentary kind of settings that the mineralization that you're looking for can be most likely flat and they're like pretty much close to the oil and gas kind of thing. So each of these things can have their own different kind of applications. Like you need to really think about that kind of mineral deposit and make sure that you are designing the right one. So here we have an image in here that you can look at different mineralization like these called feasibility studies. So these are well-known mines all over the world that the Ontario Geological Survey, they made their synthetic model. Elmo, Gold, San Nicolas. So these are the name of the mine. So we have the name of the mine, Helmo, and I put in the middle what kind of mine it is. Is it a gold mine? Is it
Right.
VMS, which is volcanic massive sulfide deposit? Is it a copper or a diamond? So no matter, like we pretty much, we like to do some kind of, so if you're any geophysical methods, you want to understand if you're going to use this geophysical method on this as like a specific area, is it going to give you the response and data that you can use and uh, pretty much figure out what's going beneath the earth. So these models were built, and there's been lots of simulation of different geophysical methods. There's a gravity, there's magnetic, and there's the EM methods, electromagnetic methods. And these are very well understood in the mining setting. And lots of people use these methods, geophysical methods, for pretty much imaging their surveys. And then they are very, like, if we're looking at this geophysical methods, seismic is the most intuitive and like most accurate one. But again, in order to see if the seismic is going to work on this ones, we got to do some kind of modeling. So we take these models and then we start like putting seismic sources on the top of these things. Everything's done in the computer, and we simulate the wave propagation into these things, seismic waves, and we can see what kind of images we can get out of these models.
Sorry, Mostafa, what do you mean by putting a seismic source? So is this it's like a computer generated simulator if you were to do a seismic
on the surface? Yeah, pretty much
it's simulating a real world application of a seismic test, right?
Exactly. So we know the equation. These equations of seismic wave propagation has been known like for 200 years. We haven't been able to record them, but like there were very smart people like, let's say, Newton, Hooke, and Riley. These people, they knew the formulas. They've been all mathematics that was developed. So in computer, all you need the math for simulating these things. So we say, okay, if I simulate this area, if I put the source in here and shock the wave, send the shock wave down, how it's going to propagate and how it's going to come back. We know how it's going to behave, and there's very good softwares that they can do these kind of simulation nowadays. So all we need to have some model which shows what kind of layers we have. So here, if you look at the BMS 12, so this is a very challenging kind of deposit, like for seismic to be able to image it. And the reason for it is because things start to be near vertical. Naturally, seismic works very well for when your layers are flat. So if you have flat layers, but when things start tilting and becoming near vertical, seismics can have like a bit difficulties, and you really need to come out with the right parameters to be able to adapt the seismic for these kind of
is that the yellow
scenarios.
And blue? We're seeing the hard rock mineral deposits. It's blue,
exactly
blue and yellow.
Here in this model, that red, like dark red part is the real mineralization. The yellow parts near it to the left of it is also a mineralization zone. So they're starting, you can see the boundary of them, they're pretty much near vertical, digging 70, 80 degrees. So we really want to see how seismic will behave in these kind of scenarios. So we take this model. So if we go to the next slide, you can see what we do. We come on the surface. Let's say this is an area of 3 by 3 kilometer. And we start putting our seismic receivers. These are the ones that they're going to receive the signal. We try to put as a carpet, like, let's say every 50 meters. It can be different. Seismic design is all about finding what's the best distribution of these receivers on the surface that we can put. So let's say for now, we can put 50 by 50 meter, whatever it is going to be. And then once we carpeted the surface with all our receivers, then we bring our source. That source can be a dynamite. So we're trying to shake the ground. It's like we're trying to send the shock waves to the earth and wait for the reflections to come out and see how far they are. But then for doing this, we're going to do many of these. So the same way that all the surface, we put like every 50 meter receivers, we're going to start pretty much, let's say every 50 meter, we're going to shock the earth. And this would be dynamite, or could be we have this huge trucks, we call them vibroseis, that they have large plates beneath them and they can shake the ground. Pretty much we're generating mini earthquakes, kind of. And
Right.
we're sending the waves down and waiting for the signals to come up.
So that's that big truck. There's a picture of a white truck with a so what is that? That truck's sorry, is that's is that putting pressure on the ground and then the explosion?
No, that just shakes the ground. So the
Oh,
plates under it, if you see in the middle, there's a
yeah.
plate. Those are like ton, like I don't know how many. It depends on the size of the plate, but they can be like 1 ton or 2 ton plates. What it does, it shakes. Like it starts with like a very low
Oh,
movement, and then it starts like shaking harder, and then that like if you're near of one of these operating, you will feel like the ground is shaking for you.
so
Like
this is separate. This is a different method other than the dynamite.
yeah,
Ah,
it's a
got it.
source of its own.
Right,
Yeah.
got it. Okay.
Dynamite, you need a crew, send the people to drill the place, maybe 5 meter down, seal it, put the dynamite inside and explode it. That would be like in the mining, they do a lot of those, but
Yes, yeah.
let's say once we do such a simulation, let's say if we did that, if we go back to that model and I see in the left side, so let's say if you explode one of these and you in computer, it will show you how this wave is going to propagate. So I have here saying 3D simulated seismic shot gather in the middle. This pretty much shows one of the shot gathers, like this one of the sources that we simulated and the wave going down. You can see it's like ripples. It's pretty much imagine you're on the lake and you throw a rock and you can see ripples going around. It's
Right.
pretty
Yeah.
much the same concept in here. It's ripples going down the surface, left and right. So, and when they hit some boundaries that there's a difference in density and velocity of the different boundaries, they come back. So they can propagate all over. And we can have like, let's say we're going to have 2,000 of these cubes. So we take all these data. It's going to be a very massive computational task in here to analyze these data, but lots of very interesting theoretical aspects been developed to process these data. But once you take these data and bring them to your computer or station or company, you can start processing them. And you can see on the right side now we have like we take like sections of these seismic. You see it's starting to look something similar to what we have there, but it's a bit different. So like you can look at time slices, let's say at depth or depth slice, let's say at 2000 meter, what's going to be like I will be seeing in seismic, and then you can compare it to the real model. The good thing with these simulations are we know what the model is, we know what kind of boundaries we have there, and we now see the seismic. Then we can see if like needs to be some modification in our seismic acquisition to get the right parameters to be able to image these kind of whatever near vertical kind of scenarios of the geological layers. So that pretty much like this kind of simulations gives you some like kind of confidence that okay, this parameters that I am going to design for seismic, I'm going to tell my seismic receiver lines to be 100-meter apart, and on those lines I want them every 20-meter seismic receivers planted, and also I want my seismic sources to be like every 50-meter, like to be in the, like cover the whole area. And with this acquisition parameters, I should be able to image my targets, let me call them targets, or mineralization zones, or anything we want to call, and then you can record them and look at them.
At Corporate Traveler, their seamless combination of expert service and innovative booking tech means you have what you need when you need it. Mining companies need experienced agents who know how to get you to far-to-reach destinations with ease, who understand rotational crew travel, chartering, and so much more. And with an average tenure of 8 years, their agents are the best in the biz and are experts at managing all your mining travel needs. Have an emergency? They've got your back 24/7, anywhere, on any device. Don't get stuck with complicated and rigid travel options. Get it done with Corporate Traveler. Visit them at corptraveler.com. Geograph is Australia's leading manufacturer of enhanced performance mining parts. Geograph designs and manufactures enhanced wear parts to suit major mining machinery from Caterpillar, Komatsu, Hitachi, Liebherr, and more. The GeoGraph Enhanced Performance range is designed to reduce downtime and operating costs for mine sites and off-site repairers by engineering wear parts to last longer. GeoGraph challenges you to expect more from yourself and your assets. Visit geograph.com.au for more information or click the link in the video description below. Introducing the SolarSet Fold. The new foldable frame solar system brings power to your residential and commercial property and can be shipped worldwide. Like all SolarSet products, the SolarSet Fold comes turnkey, pre-assembled, and is easily transported and installed. Learn more about SolarSet Fold and their full line of amazing solar systems at solarset.com.
We design it, we find the right parameters, and then we give this one to the companies that they will do it. There's acquisition companies,
And then you
and
take
they
the
have the
data that
equipment.
they gather. They do,
Yeah.
they do it, then you gather the data, and then you redistribute the data back to them.
Yeah, they will collect the data, and we will make sure that while they're doing this, we're like, as I said, when you go to the field, things is gonna be not everywhere is flat and everything. They need to cut the lines, make sure that there's no tree on your path and all that. There's a slope, and they can't put the receivers. And we need to still do some analysis. Okay, if you can't put this receiver or shot or source in here, where's the best place we can move this one so we still have the same quality of image and our image is not disturbed? So we really look at that very closely. And once that step is done, and the cutting and the planting them, and there's companies that they specialize in these kind of acquiring the data, and they do their acquisition, and then they send it to the processing company. Seismic processing company will process it, all that. They need lots of computational resources to do it, and you will end up having some kind of final image cube that you can slice it through at different depths and see what kind of anomalies, seismic anomalies you see there, which they can interpret them to what they're going to be. Is it the mineralization, or is it the oil, or is it the gas? All that kind of stuff. That's the later stages for the geologist to deal with.
Okay, thank you, Mostafa. That's a lot of information there. Optiseis, I think it's like I need to talk to you every couple of weeks just to like gain another layer of understanding. But this was quite helpful. Alyson, welcome to the show. Great to have you on. Let's start with your role. What is your sort of day-to-day with Optiseis?
I mean, it varies every day, but my role is a software manager, so I oversee the development of the software as well as a bit of marketing and sales.
Oh, okay. So, how long have you been with Optiseis?
Also a difficult question to answer. Probably about a year and a half now total. I first came as a student, and I just started the role as a software manager about a year ago.
Oh, wow. Well, congratulations. So let's do a little bit of a talk, because I really want the audience to sort of understand. I think if the audience can understand development, then they can understand application a little bit easier. So a year ago, when you started in this role that you're currently in, what was sort of the main focus? And then what is sort of your day-to-day focus now, on the development side?
So for the development of the software, over the last year, we've been primarily focused on integrating our eco-size research into the software, because as Andrea and Peter went through on the previous episode, we've been doing a lot of research on eco-size, and we want to make it so then we can be using it and utilizing on that research a lot more.
So can you just clarify again, because some people won't have seen that episode, can you walk us through EcoSize just as that development, that software?
Yeah, for sure. I actually do have a video on it.
Sure.
And so as you can see with the video, there's EcoSize focuses on many different geometries. And we are trying to integrate using these geometries more because it reduces our environmental footprint. So we consider things like habitat and species and infrastructure, and then rank these areas based on the effect that seismic surveys have on these areas, then assign different geometries for these areas in order to reduce cutting in more sensitive areas, while considering the field operations and safety access when we design these.
So so when you're building this strategy, it's not just essentially it's not just a blanket, okay, we're going to have to get this whole area. You're designing it specific to each little specific area within that mass.
Yeah, because in our eco-size research, we found that the Vibrosize or dynamites, any seismic survey affects ecosystems in different ways.
Mm-hmm.
So it affects marshes a lot more than and forested areas a lot more than an open area. So we classify them in different ways. So then maybe we'll do more intense survey on something that's a bit more open and a little bit less intense in places that are a bit more sensitive.
How would you here's my layman question of the day. How do you what is it called? The topography of the land? How do you actually, before you go there, what kind of data do you need to collect before you can even start to input the data here that we just saw in that video?
Well, usually it's from the client, but we can acquire some. So they send us some shape files based on known structures and areas in that specific study area. Otherwise, we can use like imagery from something like Google just to get an idea of the area. And the client sometimes provides some aerial imagery or some LiDAR imagery, but it's in the end, the most accurate thing is when we actually get people out there in the field and they verify what is there.
What is physically actually on the ground there?
Yeah.
Now, the Vibrosies, if I'm saying that right, the Vibrosize truck, or dynamite, how is that decided? What is the best application there?
It's a combination of things. Primarily, it's decided by the client, but we will provide suggestions based on the specific needs. So depending on their target depth and the area itself, because some areas maybe you can't drive a 2-ton truck through.
Right.
And some areas, maybe blowing a bunch of dynamite is not acceptable. So it really depends. And especially we work with many different clients from different places in the world, and regulations are different in different places.
Is developing the modeling, and I'm thinking specifically, I mean, I've been on lots of mines, not as many as some people in the industry, but I've been on enough to know the geography is just crazy. Like it is the variation in one, like you'll have a mine where there'll be a creek coming through this side, there'll be a little stream coming down here, there's a little pond over here, then there's a huge rock face in between all of that, and then there's a forested area. Like it's just so bizarre sometimes the landscapes that you'll see. So when you're going in, you're collecting all this data, then are you manually, like that through that video, is that manually you're adjusting every location based on the data, or is there some sort of AI system that's putting in the data? I'm just trying to understand the software development, which must be very extensive.
Yeah, we've done a lot of work on it, and there is a combination of things, but in the end, you're right, moving every station manually takes a lot of work. So we try to get our software to do as much work of that as we can. Since we've been doing more and more eco-sized designs, we try to put more automatic features in the software. So then we can just click a few buttons and then everything moves into the right places. Because as you were mentioning with those really steep areas, a big 2-ton truck can't drive through a very sloped area or off of a cliff. And we would not want to tell the field ops crew to do that because that's a huge safety risk.
Right. So so you're, in some cases, you might even be mixing the dynamite and the truck in multiple applications.
Yeah, and that's very seen extensively in Canada too, because there's lots of forested areas, and in order to get the huge truck through, it involves a lot of tree cutting. So we might choose to cut a few less trees and then go and put dynamite there because we don't have to bring as big a truck through there to put it in dynamite. And there's and in some cases, it might just be easier for the crew to do so. So we try to tailor it to the crew's needs as well as the area's needs while trying to reduce the environmental footprint.
Right. And what is the biggest challenge? We've had lots of different people on, but we've probably had since doing the show, we probably had 20 software developers on the show. And the challenges are always different depending on the application. What is the big challenge here over the last year that you've had to sort of focus in on in the development of this software?
For our development of the software, we've just, as I said, it was mostly Ecosize, and it's just understanding how the geometries work and how to create the ideal geometry. So throughout our Ecosize design, we've been going through 20 different iterations of different geometries. So this involves like different, the original survey, I guess the traditional surveys are orthogonal surveys. So it has sources or the big trucks or dynamite going in one direction and creating parallel lines. And then we put receivers or some kind of like sensor going perpendicular in lines to the sources. And that's the traditional way, but that cuts down a lot of trees because you're making a grid essentially.
Right.
And that's not super environmentally friendly. So we're looking at ways to reduce that. And some of those thoughts are putting sources and receivers on the same lines, which has been a challenge for our software because the numbering has been completely different than what is traditionally done. So we've had to tailor our software to accommodate for that.
So when you're gathering all this data now, it's going into a customized software. What is the like for instance, you have these exclusions. Can you actually just walk us through that? Because I kind of get it, but I don't quite understand what I'm looking at when it says examples of exclusions. Is that what stage are we at when we're talking about that?
Yeah, so with an exclusion, that's an area that we cannot bring maybe a giant truck or we can't put some dynamite. And that might be some place that is close to a building, for example, or infrastructure, because as Mostafa mentioned, with the Vibroseis and the dynamite, it creates big vibrations in the ground, like an earthquake, and you
Right.
probably don't want an earthquake right next to a building. It's not great for the foundation. The exclusions are marked as orange shapes. So
Oh, okay.
those, because typically you have to put buffers around them. For example, a building, you don't want to go within 20 meters of a building because that could disrupt the foundation. So we create big buffers around it, and that's what the
Right.
orange is. And in our software, the red square represents the source. So that could be a
Right.
dynamite or a truck. And we can move those outside of the exclusions really quickly. And you can select every single point and just move them all out of the excluded areas at the same time. It's just very efficient. And when we have so many surveys to do in a year, it makes our job easier. And we're hoping that it can make other designers' jobs easier too.
That's what I was going to ask. When you said when you can do this and you can do that, is that you Optiseis, or if I'm the client, can I do this as well?
Well, it depends on the service. We have a consulting company, so we do these designs on our own as well
Okay.
for our clients. And we have some clients who are also designers and they'd prefer to do all the work on their own. So they can get a license for our software and then just do all these easy movements on their own.
Right. Oh, I see. Okay. So it can kind of go in both. Okay, so there's another video, Alyson. It's titled Line. I'm going to bring that up right now as well, because can you just walk us through that? Because it seems like it's similar, but maybe you can kind of see actually some of the things that are involved, because it's more of like an on surface shot. Can you walk us through that one?
Yeah, for sure. So in this scenario, we can see that the line of sources in red are right next to a road. And in some cases, you might not want to be right next to the road because you'd be cutting down a bunch of trees when you can just move it a little bit over and then it's on the road and not having as much of an environmental impact.
Right.
And if you have a shape, usually roads have some kind of shape file, whether you get it from a free data or from the client, and you could easily just move it from its original position onto the road. And it can be used for so many different applications when designing a survey.
Right. Someone like me, I'm here trying to unpack it for a very large audience. But when you're talking to people, how what is their depth of understanding? Are they asking similar questions to me, or are you talking to people that already have a really good understanding of seismic, and now they're just seeing that next level that Optiseis can take you to? Alyson, we'll start with you on that question.
Well, I mean, it depends on the situation, of course, but most of the people I talk to are clients who use a different software, and they're trying to think about switching to our software. So they do the exact same thing on a different software, and they're trying to understand and compare how our software is different from competitors.
Right. So I should have clarified. Is this in the mining space as well, or do you have clients that are new to using this type of software, any type of software in the seismic space, in the mining sector specifically?
So we deal with clients in the mining sector as well as oil and gas, and they typically already have design experience,
Right.
and they're familiar with creating surveys, so they ask very high technical questions.
Right.
And very specific questions because they want to do something that they're used to doing in another software in our software.
Maybe I'll expand. Oh yeah, sorry. Go ahead, Mostafa.
Yeah, I just like talking about the seismic and mining section. It's like as I said, the seismic is well understood for anybody that works in oil and gas.
Exactly.
And
Yeah.
pretty much works very fine. In the mining, it's not been a mainstream, and people they usually, and there's a reason, because most of the mines that people can mine, they are usually at the surface, closer to the surface, 100-meter, 50-meter.
Mhm.
They might be able to drill it everywhere. Lots of our oil reservoirs are 2-3 kilometers below. But now, like we pretty much depleted all of those simple mines. Our mining exploration is starting to go deeper too.
Mhm.
So now people are starting to understand the value of seismic that can
I
give you
see.
images from deeper parts. So again, most of the people that we will talk in the mining company most likely will be geophysicists. There might be some kind of CEOs stuff too, but they will have some geophysicists there that would like to work with us. And again, we need to pretty much, with some kind of our simulation studies, all that, and the computer modeling, we should tell them that the seismic will provide some value for their imaging. So we will try to bring them in, say, okay, give us your target, what kind of layers you're expecting. We will do models and we generate our seismic data, and then we communicate back to them, okay, we might be able to design a seismic survey for this specific target that you're interested, and we can image it for you.
That must be a huge, it must be a huge attraction though for the mining industry, being like mining right now, as a lot of industries, they're really trying, you know, their ESG goals and things like that, and trying to, you know, their relationships with indigenous communities around where exploration is happening. I mean, these are real. There's some real opportunities, but there's also some real challenges with it. Is that a big value add then, if you're going to, you know, if you're going to take, I don't know, 50% less trees than you normally would?
Definitely.
Is that hard to communicate to them? I guess another way of asking, is it hard to communicate, or are they able to see this software really quickly and know, oh, I get it. Okay, I get that it's going to be 50% less trees. Or is that still a challenge to communicate to the mining industry?
No, the cutting part would be simple, because right away we put the geometry, we will show where the lines are going to go, and we know it's going to be 2-meter cutting of the widths of the lines, 2.75. Those are the standards. That's easy, but the hard part is to convince them the image that they're going to get of this design is going to be comparable for the grid one, what we call the orthogonal one. So that's the hard part. So the EcoSeis that my colleague Alyson mentioned in here, EcoSeis array, we have done many of these simulations. We had a very dense grid that we decimated in different geometries with less, let's say, line cuttings and stuff. And we did them, and out of, let's say, 20, 30 simulations we picked few, 1 or 2, that they really come up with the same image quality. So once you have such a thing and show that the geometry that you're designing with less tree cutting, it will generate them pretty much the same quality image, then that's the tipping points, and they will say, okay, that looks like it's going to work. So you convince them to do the seismic with this new geometry that you're cutting less trees. Nobody disputes that cutting less trees is bad. So everybody likes
I don't think you're going to get a lot of debate on that one. Okay. Mostafa, I want to bring you back in, and Alyson, please feel free, both of you, to sort of jump in or throw it over to the other person as we try to walk through it. I got sent a bunch of graphics here. This sort of like the source, the receiver. Alyson, you mentioned that earlier, and it's called the seismic reflection method. Mostafa, I think I'd like to start with you. Can you walk us through a couple of these graphics that we're seeing, just so the audience can kind of gain a better understanding?
Yes, yeah. Here I try to, like, in a simple cartoons, show what the seismic like really does, like how would we do it. So we usually, as I said, we want that source of shock wave that can go down, and ideally we would like our receiver to be right at the exact location there. But as you might have noticed, that the dynamite and that huge trucks, you cannot put the sources and receivers at the same location. So we send these signals down, and depending, here rho is the density and v is the velocity. So if there is a difference between this rho1 v2 multiplication of two layers, you will get the reflections. We call them impedance difference. So these reflections we will come back and you will record there. But as I said, it's impossible to do it at the same locations in a way. So we spread these things along a line. So we put a source, and then you can see we put like receivers to receive the signal from it to the right of it. Could be like as many extent we want to go.
Right.
But once you do many of these shots, you will be able to pair them. So you can choose a pair of shots and receivers that they're just bringing pretty much the signal from the same location from subsurface. And that would be the image in the middle and the bottom. So you can have pick one source and the receiver that they pretty much bring in the signal from the same location. But what ends up being like this, rather than we will end up, as the farther the source and receiver get from each other, the reflections is coming, it's going to come at the later time. So it gives you these kind of curvy looking, we call them CMP gathers. So things start to looking like curved. As the farther the distance and shots and receivers are, they come at later time. So these are hyperbolic in nature. So what you need to do, if you go to the next slide, this is like a crash course on seismic processing.
Great.
You can take these curved events. We know how far they were from each other. We have some guess of the velocities, and we can guess that, and we can pull them up. So in this image on the left, you will see these different events that they're coming from different pair of source and receivers, and we know how far they were from each other, and we pull them up. So you will end up lining them up. So you will have, let's say, 80 or 90. Here is a 5 traces examples. You might have had like 300 of these. And that's the value of seismic. You can deal with the noise. If you have a noisy environment, you're collecting these data, while these things lined up, then you can sum them all up, and they will just going to give you a bright reflection that you're interested. And that will sit in the image where it belongs to, and you can image it. That's one part. There's another important aspect about we call it seismic migration. Usually, let's say if we just simulated this thing, we were in the same locations, signal is coming back to you, it usually comes back in a 90-degree. Let's say if you're throwing a ball to the wall, it will come back to you if you were throwing it at the right angle. It will go the other way. So if you have a sloping event, now we're talking all these mining, that you have all these near vertical or sloping layers. So the signal is coming from to left of you. The blue color is the location of that one.
Yep.
But our geophones thinks everything's coming from right beneath them. So that you will end up in the seismic record seeing something that dashed green line, while more the reflections were coming from that blue line. So that's the location of it. And this is a seismic processing, we call it seismic migration. So we need to shift these things to those locations. Anyway, this is a processing concept, but that's something that you need to keep in mind when you're doing seismic. And if you go that, like these are examples, I have next slide, I have examples of CMP gather.
Yes.
So you will see these colors coming, popping up. So these like negative and positive values, like we call them wavelet, that for the sake of them, we're not really important, but anything that you see the color changes and there's like something, those are reflections are coming. Those are 2 CMPs. But as I said, you got to sum them all these up, and then you will get single trace. If you see on the left side, we call them seismic section. And that will, when you put many of these side by side, you will end up getting that seismic section that shows you where the layers are. And this one you can see on the left final process seismic section. We have the layers that all of a sudden at some to the left, the reflection going down and up. So you will pretty much get some this kind of images from using seismic. And just a final real 3D seismic, the examples that I explained in here, they were for 2D line. But as I said, in real nowadays with the seismic, we do them in a surface. So rather than in a single line, we put the source and we have receivers all different sides of covering the different area on the surface. And you can see here the red dots would be, this is a real survey from, I think, Queensland, Australia. And then you can see how the surveys are end up being. So red dots were anywhere locations that we might have dynamite or vibrosize. And the blue dots that you see here, those will be where we had the receivers,
Right.
and we recorded on those. And then that goes from this point on. Once we acquire the data, we send to the processing companies, seismic processing, and they have lots of mathematics and algorithms that can really deal with these data and generate those images that the people interested in.
Alyson, do you think you could just expand, just kind of try to tie it together with the from the software side, from the what we just walked through? Then can you add on sort of your software development side onto that?
Yeah, for sure. So we keep track of these midpoints that Mostafa mentioned. So the software calculates with every pair of the source and receiver where the midpoint would be. And that's the point where the data is actually coming from. So usually you don't want one point in each area. It's good to have more than one just in case something goes wrong with one of those data points. So depending on how deep you're looking and what you're looking for, you might want it to have a higher density of points or a lower density of points. And as you can see with this image, our software does keep track of all those and calculates it. And even after you move a bunch of stations. And one thing that's unique about our software is that we have an optimization algorithm which tries to increase the amount of points in certain areas of the software of the survey. So for example, if you cannot go in a specific area because there's a huge lake there, or maybe it could be anything. So there's something in the way and you cannot go into that area, then you have a lack of data there.
Mm-hmm.
So, and there's nothing you can do to go in it. So we can add extra points around it in order to try to get more midpoints in that area.
I see. So you're basically you're sort of doubling down on the surrounding area to maximize data points from it.
Yeah, and our software will automatically calculate those areas where you can try to focus those data points on the center where you cannot go. And you can see in like the images here, after we do optimize these locations, then we can see that there's a higher density of points in the center.
Mm-hmm. Yep. That's that sort of purple, right?
Yeah.
Yeah. Got it.
Well, you can see with that first image, there's that hole in the center because it's not getting enough data. And then the second image, it looks a bit more uniform in the center. Mm-hmm. So it shows a more even distribution of data.
Right. No, it's amazing. It's a lot. I mean, and I realize that if you were talking to, like a geologist or someone from the field, I mean, they'd probably be asking some different questions. With that said, I do think that I am not the only one. I've seen people having these types of discussions at like trade show events, and they've got this glazed over expression on their face. So I know I'm not the only one who doesn't have like a really good understanding. So I think the way you actually walked it through, and there's actual graphics and the 3D images and the videos actually showing the software. I can't tell you how many times I've seen screenshots of software without it actually working. So it's very hard to show the audience what you're doing. It's very helpful. Before I let you go, we mentioned carbon capture at the very beginning. And I don't know who wants to take this one. I just wanted to quickly touch on that before I let you go. Who wants to start?
I can explain that. this carbon capture utilization and storage, like sometimes they drop the storage, but like CCS. So we nowadays it's mainstream in our oil and gas industry, and it's all about pulling this SCO2 from surface, like from our operation, and inject them into some reservoirs deep down and letting them there. So it's all about reducing our CO2 emissions. So to do these things safely, you need, let's say you picked up some reservoir at the depths of 1 kilometer or 2 kilometer deep, and you're injecting these things. So you got to make sure that what you're injecting is staying there, and it's not like going through some faults or breaks, gonna make its way again back to the surface, and you will spend all this time and energy to put this CO2 back and into earth, and lock it into the reservoir there, and all of a sudden it breaks back and comes up. So seismic is pretty much the best tool to monitor these kind of reservoir CO2 sequestration and storage locations. And there's so many. So you can do our regular surface seismic, the one that we were talking all this time. You can do what we call something called microseismic. It's just like monitor cracks on this subsurface and where they're happening. You can do something called vertical seismic profiling, because you already drilled to inject something, and you will drill another well that monitors that one. And there's some cross well seismic. You can do sources in the monitor one or sources on the ejecting one and record that. And all of the purpose of these ones are making sure that what we injected in that reservoir and deep down 1 kilometer or 2, whatever that reservoir sits, it stays there. So CO2 is not making its way back to the surface. And that's kind of guarantees or some kind of assurance that the CO2 that we injected there will be staying there and will not be making its way up. And seismic can definitely play a very important role in monitoring these kind of projects and reservoirs.
And Alyson, on the software side, it's all the same principles and that, or does it get adapted a little bit when you're trying to do like a carbon capture data gather?
It's the same principles. The only thing that varies is the target depth. So sometimes that's different in different areas. So oil and gas, mining, and carbon capture all have different depths of targets. So and our software can account for that because it is adapted to all target depths.
Mostafa, Alyson, thank you very much for coming on the show. It is Optiseis. I started talking to Andrea about 2 years ago, and so I get to do this job as a student of the industry. So thanks for taking the time, and also I just wanted to give an extra thank you for leading up to the show, taking the time to lay this out and put graphics for me and all that sort of stuff. It makes a huge difference because we do want to educate the audience and help them understand what's going on. There's not just mining people watching, it's other people outside the industry, and they're getting more and more understanding all the time of what's actually happening. So thank you very much for taking the time, not just on camera, but off camera, to help put this episode together. Really appreciate it.
Thank you. Thank you.
Thank you.
Our pleasure. Thanks.
Thanks for having us on the show.
And thank you. And thank you everybody for watching Mining Now. This type of episode was actually a key part of why we decided to make this show. We sometimes do high level, but a big part of it is to dig in deep and try to figure out this technology that's within the industry. So thanks to Optiseis. Thank you to the audience for watching. Thank you to to Corporate Traveler Canada, Savanaugh Equipment, for helping us get all over the world. Love doing the show. We will see you on the next episode of Mining Now.